You know this famous, the origin of graph theory, and when you have that about the bridges of Königsberg, when it was the beginning of the graph theory, and Euler had this, that the question was to pass through, for example, each bridge exactly once. So, for example, if you have 4 vertices, 1, 2, 3, and 4, and you have, for example, this graph, and maybe this graph. So you have possibility, if this is maybe A, B, C, G, E, maybe I have to make it Eulerian, otherwise it doesn't work. So here, maybe I put here, but here the multiplicity, I need something, maybe this one, in order to make it. So you have here multiplicity 3, 2 minus 1, here you have 2 and 2, here you have. So you have the possibility starting from 1, for example, this is F. So you can get A first, then you can get F, then you get B, then you get D, C, and A. This is a path which goes exactly 1. Or if you write the number of the edges, you get from 1 to 2, from 2 to 1, from 1 to 4. Then you go back to 2, back to 4, back to 3. And of course you have some other possibilities. First, to start with maybe this one. The other possibility is if you start, for example, from 1 going to 4, then you get to 2, to 1 again, then you get to 2, you get to 4, and you get to 3. You have 2 Eulerian paths starting from 1 and finishing at 3. You have no more other, of course, by the theorem of Euler. And now, if you have a product so if you have a product, if you take the standard polynomial S twice n, and you replace here by 2n matrix units, so this is simply a sum. Here you have the sign, where sigma belongs to twice n, the symmetric group of degree twice n. And here you have E, you have I sigma 1, J sigma 1, E I sigma twice n, J sigma twice n. So this is equal to the number of paths which are corresponding to even permutation starting at EI and finishing on J. I write here sum minus a similar thing, but here you have odd permutations, and you multiply by the matrix unit Eij. Here the sum is on I and J. This is the result. Because if this is not 0, this means that you have a path. If this path corresponds to an even permutation, this is with sign plus. If this corresponds to an odd permutation, with sign minus. And you count the paths. And the theorem of Swan was that for an Eulerian graph, oriented graph with 2n edges and n vertices, the number of even paths is equal to the number, even Eulerian paths, of course, is even to the number of odd Eulerian paths when you count the same points, the same origin and the same end. So this simply means that you have exactly this part here, they kill each other and you get 0. This is the proof. For example, if you have two vertices, you consider this possibility. You have here. So this is the first vertex, this is the second vertex. So I write here, this is x1, x2, x3, x4. This is the first vertex, this is the second vertex. If you follow all the possible paths, you have x1, x2, x3, x4. And you have the other possibilities. You start with x2, you go with x3, x4, you have x1. This corresponds to starting from 1. So this is when you start to 1 and you finish at 1. And of course this is positive and this is negative, because here you have an odd permutation. If you start with 2, you have something similar. If you start with 2 and you finish with 2, you have here, either you start with 3, then you go 4, 1, okay, this is x3, x4, x1, x2, or you first go x4, then you get x1, x2, and you finish with x3. So in this case, this is odd and this is even. So again, here the result is plus e1, 1, minus e1, 1, and here the result is e2, 2, minus e2, 2. So this both cases you have 0, and this gives you the proof in the case of 2, an illustration. So I think that this proof is really very nice and very constructive. You take some graph, you move some edges, you move some vertices in order to make the things easier, and finally you get this. You have a lot of cases. For example, one of the cases was missing in the original paper by Swan. Then after this, there was an addendum to the paper. But I want to give you the proof by Rosset, which is really it has, if you translate this in modern words, it has some super taste. It's more super proof instead of normal proof. So the proof by Rosset, proof of Rosset, this is the following. We take matrix algebra, consider matrix algebra with entries from the Grassmann algebra. So we consider, so this is the matrix algebra with entries from the Grassmann algebra. You may think that of this as the tensor product of the Grassmann algebra, matrix algebra over K, if you prefer this way. And the first observation is the following. So we want to show something here. The first observation is that it is sufficient to prove the Mitsur-Levitsky theorem for K equals Q only. Because you see, if you consider the elements of Mn K are linear combinations of units. If you evaluate the standard polynomial with some matrices, this is also a linear combination. Here the R's are matrices. They are linear combinations of the standard polynomial when you have here matrix units. So it's enough to consider matrix units. Of course, if we know that this is 0, then we can prove this for any field of characteristic 0. So if M and Q satisfies S twice n equals 0, then the same holds for K of characteristic 0. And if K is of characteristic P, you have something similar. If this holds, then you have also M and Z satisfies the standard polynomial. So you can work with integer coefficients. Then you work modulo P. And the same holds when K is of characteristic 0, of characteristic P. So it's enough to consider the case of Q, or the case of characteristic 0. So here, this is the first observation. So the second thing is that we assume that the characteristic of K equals 0, and we want to prove, to use some fact, that if A is a commutative K algebra, and if R is a matrix with entries from A, such that the trace of R in power K small equals 0 for K 1 till n, then the n degree, the n power of n of R equals 0. So if you have a matrix with n by matrix with entries from a commutative algebra and all the traces are 0, then the n power of the matrix is also 0. So this is almost an exercise on symmetric polynomials. But you see, if A is any, you consider if the matrix R, this is some element which is Aij, Eij, where Aij they are from the algebra. Of course, we can assume that we can consider another matrix S, which is a matrix from, and it's from the polynomial algebra in n squared variables. And if we prove this, if we prove for S, then we prove this for R, because you simply replace the elements Xij with Aij, and the trace, this is obtained by evaluation of these elements. So it's enough to prove this for polynomial algebra. Of course, you can embed this, the polynomial algebra, in its field of fractions. The field of fraction can be embedded in something algebraically closed. So we embed this in the algebraic closure of this field. And we may consider that S is a matrix with elements from an algebraically closed field.